All right. So we're going to start out talking about computer memory and arrays. However, today we're going to be talking about computer memory, which will, as we'll learn, necessarily involve talking about arrays. And we're going to dive deeper into the linked list data structure. We got a bit of a preview of it in our last lesson, and we're going to go a bit deeper. So we're going to learn about different kinds of memory, how memory is organized, why arrays are fundamental data structures because of how memory is organized. And then with linked lists, we're going to review what a linked list is and why it exists. And we're going to see how to do some common operations like adding a node to the beginning or end of a linked list, finding something in a linked list, and if we get to it, deleting something from a linked list. And the goals are really twofold here. One is gaining a stronger understanding of how computers work, which will help you as you move forward in your careers and think about your programs. And also learning these linked list manipulation skills, which are good to know, but are especially useful in case you see a linked list in a technical interview. We're also going to learn a little bit about how Python manages memory. Do folks have any questions before we dive on in? Cool. And I apologize for not getting this out to folks sooner. And let me see if I can't get. There we go. That's going to make life so much easier. But our curriculum has been updated, and so everything we'll be moving through here is in this memory and linked list lesson today. And we're going to be starting out talking about computer memory. So computer memory is really cool. I'm going to talk a little bit, but not a lot, about hardware. And we're going to talk about the different kinds of memory. So, obviously memory is where a computer stores everything, right? Where a computer stores data. And there's a saying, code is data, right? I think we all know that, a CSV file is data, a cat pic, right? An image file is data. Any file of any kind of different format that gets saved is data. But also, every single program we've installed on our computer is data. The operating system itself is a program, and that has to live somewhere in computer memory. And when our program is running, we're creating data all the time, which, we've seen whether it's with Python Tutor or the debugger. So like currently running programs and all the data, created by them are all stored in computer memory. And then even things that we might not immediately think about, such as input and output, such as when I press that key on the keyboard or I move my mouse around, right? Or I draw on the screen and the computer needs to remember which pixels are now red. All of that is data. So there's two kinds of memory. There's main memory and there's secondary memory. Main memory is often called working memory. And if we were to use the analogy of our brains, this would be sort of like our short-term memory, because the things that the computer is immediately doing, like keeping track of what's being drawn on the screen and keeping track of where the mouse is moving, the computer needs to be able to access that information very quickly, right? Otherwise, computers would be incredibly slow and useless. So main memory holds stuff that the computer is currently doing. RAM is the classic example of main memory, random access memory, when you read computer specs and it talks about like 16 gigabytes of RAM versus 32. And that's why for those of you who have Mac laptops, you could have like a massive hard drive with 2 terabytes. But if I only have 8 gigs of RAM, and especially since Apple doesn't allow for us the way to add more RAM, my computer maybe starts to slow down, right? As programs get really big, if I don't have enough RAM, then things start to get slower. Main memory, like RAM, is what's called volatile memory. And that means that when we turn the computer off, when there's no power running to that memory, whatever's in there is lost. Right? So main memory is volatile. We can't depend on saving something there long term. The CPU also has cache, and there's lots of different little caches in different places on the computer that are even faster than RAM and even more expensive, right? And main memory is volatile. It's faster to read to, faster to write to. It's more expensive and it's smaller. And I just want to pause and check in and see if folks have any questions around this idea of main memory or working memory. Awesome. And I'm just curious, for a quick show of hands, I know this is probably not new information and it's review to some folks, and it's probably new information to some other people as well. Who is this? For whom does this have some new information? Just so I can kind of see. Okay, awesome. So it sounds like this part is going to be a bit more review. Secondary memory is storage, right? What we call the hard drive. And these days, it's normally a solid state disk, which is the image you see up here. Sometimes maybe there's still actual hard drives, which is what this used to be. And the difference, right, is the hard drive actually has a spinning platter, just like a record or a CD. And like it's magnetic somehow. So there's a little playhead, and it's literally like tiny little magnetic bits that get flipped to ones or zeros. Secondary memory is not volatile. It's non-volatile memory, right? When I save something, when I save a file and turn off my computer and turn it back on again, the file is still there. And that's because the computer saved it in secondary memory, aka storage. It holds data not currently in use, like your source code, like the binary executables for all the different programs we're not currently running, and the operating system itself. Sometimes the computer does what's called virtual RAM, where it uses a part of the hard drive, a part of secondary memory, to maybe store something actively running, which is slow, but maybe I've got if I had iTunes open right now, but it's in the background, right? Maybe that gets put into virtual RAM. So secondary memory is slower. It takes longer to read to, it takes longer to write to. If we were storing, what's being rendered on the screen here in secondary memory, then it would take forever. But secondary memory is also a lot cheaper and it's bigger, right? And cheaper is the reason why we don't just see tons of RAM or like massive CPU caches. One of the reasons. So then there's also external storage, offline storage. These images I put together a nice little sort of computing history 101. Way back in the 60s, this is what a computer program looked like, which must have been a nightmare. It was a series of punch cards that said, like move index 12 value to index 24, increment index 24 by 9, and people would have like giant stacks of these, and they had to be in order. And if you got your punch cards out of order, like that was a disaster. Here we see magnetic tape, which is still used for some backup and storage. And remember that a non-solid state hard drive is also magnetic. Floppy disks, CD-ROMs have kind of gone away the way of the dodo. USB sticks, right, and external hard drives are still around. So here again, this is just the same as secondary storage. It's even slower, it's even cheaper, it's even bigger. So this is a simplified diagram sort of how the CPU, the main processing unit, talks to memory. And we've discussed the different things that get stored in memory, and you can maybe imagine where they get stored. And the one thing I want to point out is here, the CPU, it has cache, right? It has some secondary memory that, and it's separate from RAM. And actually, modern computers have lots of caches all over the place. And then this memory bus, we don't really talk a lot about computer architecture, but there's a saying, everyone gets on the bus. And what that means is that at the end of the day, every single bit of information for everything for the computer needs to get to the CPU, and it goes over the bus. So if you have like, and somewhere when you read about computer specs, you can read about like the size of the bus, because a big bus obviously allows for more things versus like a small, narrow bus, right? That only allows for one or two things at a time. So this is another limiting factor when we think about computer performance. And I just want to pause and check in and see if folks have any questions or things that you're curious about. And let me lower my hand. And give me just a sec here, folks. There we go. Okay, awesome. So computer memory, we can think of it in a sort of a hierarchy, and you can see all the different kinds of memory we've discussed. Processors also have what's called registers, because the CPU, you know, it's probably not going to use RAM as I'm like actively drawing and as I'm actively streaming data, right, over Zoom, over the internet. That's all data, and at some point it needs to be stored somewhere. And so a lot of it probably passes through processor cache and maybe processor registers. And as you can see, there's a trend here of the faster we get, the more expensive it is, the more smaller it is. So computers are designed to kind of be smart and prioritize what gets put where for everything to run, right? So we have the processor cache and this stuff, and then we have RAM. At that point, we have really, this is secondary storage. I don't know why they put flash USB memory there. And then this is external storage here, which is obviously going to be the slowest. So I just want to pause and see if folks have any questions sort of about this big picture overview of computer memory hardware and sort of like the basics of what computer memory is. Cool. How are we feeling? Are we starting to get kind of warmed up and get our brains back into data structures mode? Awesome. I'll take that as a yes. I see a couple nods, a couple maybes. We're about to get there. So the plan is, we've talked about sort of this high-level overview of computer memory. We're going to talk a little bit about the array data structure and why it matters for computer memory. We're going to run a little bit of Python code to see what Python is doing in terms of memory management, because it does a lot for us. And then we'll take a break, and then we'll dive into linked lists where we'll be all about writing code. So let's talk about arrays. So arrays are important because of how memory is organized. And the important thing with computers and computer memory is everything needs to be organized and consistent so that the computer knows where to find things. So you can fundamentally think about computer memory as a giant grid. right? Because if we have a grid, it's very easy for us to identify any spot on the grid. And so what we're looking at here is maybe one row in a giant grid. And what's very important is that each of these spots in memory are exactly the same size of 32 bits, right? 8 bytes. This starts to become important because this way, if I know this location in memory, I can just, like at a very low level at the computer, say, okay, I have address 0, add 32. Let's get to address 32. And the same thing to get to the next, and so on. It's like if I'm on the block of a street and, someone tells me, hey, like, Adam, come on over. I'm like the third house down, from the corner of Broadway and Manchester. Then I can find this location in memory relative from this address. And that's why it's really important that memory is organized in a consistent way and where each unit is of the same size. And that's what you'll hear when we talk about a 32-bit architecture. It's the standard size of a single slot in memory for the whole computer. And we can actually run some Python code and see this. So let me switch gears and just very quickly I'll just bring this up here so I have it as my reference. We're not going to do anything fancy. We're just going to make a variable. And we're going to use this Python function ID. And if we hover over it and let's see what VS Code tells us about us, it returns the identity of an object. And remember, everything is an object in Python. And we can also look at the hex that will convert that value into hex, which is how it's actually stored in memory. Or rather, often that's how memory addresses are referred to, is with hexadecimal. So somewhere in that giant grid of computer memory on my laptop, there is a block, so to speak, with this address, and this variable lives in there. We normally don't have to worry about this with Python, and in a couple minutes we'll talk about why, but it is nice to see this. And we've seen this when we've printed objects before, when we get that not very useful thing with the memory location printed out. So stuff actually takes up a lot of space on a computer. There's what, 20, I'm gonna feel so silly, 24 letters in the alphabet, but there's a whole bunch of different possible characters, right? And in fact, let's actually look quickly at an ASCII character table. So this is a list of all the different possible characters. And as you can see, there's decimal value, but there's a hexadecimal value. There's a symbol. And a lot of these don't even have anything to do with like the letter A or B or C. Things like line feed are from when computers had to print stuff out. But you can see like backspace, right? That's a character. We can see here's all the different printable characters. And if we look in particular at the binary representation, and let's make this really big. That's too big. let's find, here we go. Let's look at over here at the number 1, right? The symbol 1. Let's look at this binary representation. This is 8 bits, right? I've got 1, 2, 3, 4, 5, 6, 7, 8. 8 bits, 8 binary zeros or ones is 1 byte, right? So from the perspective of the computer, every single character always takes up 1 byte, right? Because the computer has to allocate that much space, because it could be any possible character that we're putting into memory. And I just want to pause and check in and see if folks have any kind of questions around that. And if that kind of clicks with everyone's kind of understanding of computers and strings and characters and how these things get saved into memory. Okay, awesome. And let me do a quick check on X-ray questions as well. So where we're going with this is we look at this now, and in our scenario, it's taking up more than 1 byte. It's taking up 4 bytes, 32 bits, right? And because I think Unicode has more characters than ASCII, but the point is to store a string, we need to allocate a bunch of blocks of memory, right? Because even the word hello, even this string, hello, can't fit into a single block. This is where arrays come in. And the confusing thing here is JavaScript has something called an array. It is not actually an array data structure. A JavaScript array is really a lot more like a Python list. It's some sort of list-like data structure that for some reason has been chosen to be called an array. Because the array data structure is really fundamental because of how memory works. Everything in an array has to be of the same type. Like this is an array of numbers. The example we were just looking at might be an array of strings. An array's size is set from the beginning. This is the great thing about high-level languages like JavaScript and Python. We don't have to think about this, but like arrays are actually, like if I run out of room in this array, I might have to create a new array or use a special operation to add more to the array. And the way the computer works, I just can't add like maybe one more unit. I might have to add a whole block. Right? So usually when you need to increase an array, you double its size. So everything in an array has to be of the same type. Oh, excuse me, let's do that a bit better. Its size is set from the beginning. And this is because in memory, it's a contiguous set of blocks. And this is great because, we've all worked with JavaScript arrays, and it's similar enough that we will have an intuition about this now. Our array index 0, 1, 2, 3, 4. Well, the way it works is maybe the memory location for this very first thing in the array looks like that in hexadecimal or whatever. And then this is not really good proper hexadecimal, but I think you all can kind of get the example. When the computer allocates memory for an array, all it needs to keep track of is the very beginning of the array, because each block in the array is the same size. And so when we say, hey, get me the second index in the array, the computer just has to be cool. All right, the array starts at XABC 1, 2, 3. Each block is 32 bytes long. So I'm just going to add and do some simple arithmetic to get memory address. Oh, XABC, right? 1, 2, 3, 1, 2, 4, 1, 2, 5. Okay, that's your element in the array at index 2. I was about to say the second element, which is not correct. And then the computer can send that information back. And this is a constant time operation. That's not going to be very useful. Let me just delete all this stuff. Right, so grabbing something from an index in an array is big O of 1. And that's why JavaScript arrays are not true arrays. And hopefully this kind of illustrates why arrays are such a fundamental data structure for computers and computer memory. And really, like all these other data structures that we use, it's arrays and stacks. Really, everything is built on arrays and stacks. So I just want to check in and see if folks have questions or things that you're curious about. Okay, how are we feeling? Are we feeling pretty good? Awesome. We've got a little more sort of conceptual discussion, and then we're going to write a bit of code just to see how Python deals with things in memory. Though Python probably has some sort of binary array object. I actually have to check. That would be cool to see, but we're probably not going to see that today because we work with lists in Python. And as we can see, lists do all sorts of amazing things for us that we may not even have been thinking about. But under the hood, at some low level in the computer, it's turned into probably arrays, or as we'll see soon, maybe even a linked list. And so this is sort of a wordy description of what I was just talking about, that like because an array is a contiguous block of memory, we can get any index by taking the start of the array. We just add the index desired. If we're talking really low level, like 0, 1, 2, maybe our array isn't 32 bytes long, maybe it's 8 bytes, right? So this is why everything in the array needs to be of the same type in terms of how the computer works at a really low level, because we're gonna, figure out how far we need to go and multiply it by how big each block in the array is. And so this is what makes like grabbing something from any index in an array a constant time operation. And let me just get a quick show of hands. Who has maybe previously done a little bit with like a different programming language where you had an array data type that you actually like had to allocate and have dealt with this maybe a little more directly? Len, yeah, what was your experience with that?
It was C++. I mean, that's like, your bare metal. It's like the arrays there.
Yeah.
And as you're saying, when we get to linked lists later and pointers, like managing that memory. I just remember in class, we had to build your own linked list. And at the end, they're like, now just use this library. And you were just like, you son of a gun.
Yeah. Yeah. And then it's like, well, let's just use Python.
Right. Yeah, Python gets built on top of that. And when it first came out when I was first interested in the 90s, it was like, oh, this is object oriented without having to think about memory. And it was really kind of groundbreaking.
Yeah, exactly. My schoolwork for my CS degree was in Java, which is similar to C++. C++ and Java are both object-oriented folks, so in that sense, very similar to Python. They're what's called static, strongly typed languages, which means you have to declare like variable x as an integer and you can't change it. And then you also have to compile them before you run them. So I would have to write my code, compile it, and run it. And Python, the Python interpreter or runtime does all that for us. And Python and JavaScript both do that and are called dynamic languages, right? With, I think it's called like runtime compilation, or just-in-time compilation, maybe. But point being, it can be a little weird to be like building a linked list in Python when we already have this amazing list data structure. But the reason is to kind of learn and understand this stuff. Because one day you might work with C++ or even more so C, where you actually have to allocate memory for every single variable that you create. And also because these concerns don't go away. If we're Netflix and we have, you know, the Lord of the Rings director's cut, that's really big. We we have to start thinking about memory management for things like that, right? So even if it's not for these programs, in your jobs when you're working on like a big system, these same concerns will arise. So I just want to pause and check in and see if folks have any questions. Okay, awesome. Let's write a little code, and then we will take a break. And then after that, we'll look at linked lists. And thought I had all my screens set up here. There we go. So we've kind of walked through this. We've talked about arrays. We've talked about how computer memory is organized. We now understand why arrays are so fundamental and why JavaScript is annoying because JavaScript arrays are not actually arrays. Let's talk about why this stuff matters and play around a little bit with some Python. So, because the reality is, so Python, and for that matter, C++ and Java and JavaScript, these higher level languages, they do what's called memory management for us, or what's also called garbage collection. When I'm writing my code, you know, if I was writing C code, at some point I would actually have to deallocate this variable. And in Python, and we'll see this in a minute, I think there's actually a delete operation, which will actually deallocate that, you know, those 8 bits of memory used to store X. Python and JavaScript do memory management, or what's called garbage collection, cleaning up the garbage. Like as our program keeps on running and doing stuff, like after a while, if we don't use X anymore and nothing in our code is referring to X, the Python runtime will deallocate that for us. So we get a whole lot of great stuff for free that like back in the 1970s programmers had to do. But as I mentioned, you know, if you're a software engineer at Netflix, all of a sudden, because you're dealing with much larger scale, you still have to think about these things. And even with Python, as programs get bigger and more complex, and you know, if we're working at Reddit and writing some Django API, we might need at certain times to make sure that parts of our Python code are really efficient and performant. And it's just, I think, the principle of understanding what the computer is doing. Like our job at the end of the day is to understand as completely as we can exactly what the machine does when it executes our code. So understanding this will help with efficient memory usage and reducing memory consumption, which really does matter for scalability. And this matters for JavaScript too, running on, say, my grandmother's really old laptop with Internet Explorer 5. You know, if you all have ever gone to a government website that's gone incredibly slow, you've experienced probably some JavaScript code running in your browser that's not using memory very well at all. So we've dug under the hood. Let's talk about when we create a list in Python. And let me go ahead and let's just make a list right here. So now when I run this code, and let me go ahead and comment these print statements out. Even though we didn't do anything with this list, the Python runtime still had to ask the operating system, right? My Python program talked to is being run by the Python runtime. And so then the Python runtime talks to Mac OS X, my operating system, and say, hey, I need 8 bytes for a list. Or maybe it's 64 bytes for a list. And my Mac operating system says, cool, and gives it a tiny, tiny chunk of RAM. The truth is, as soon as my program starts, the operating system probably just gives it a big chunk of RAM to use as its playground, right? And then if it runs out, it'll give it more. So I can append, maybe if the initial size of this list has room to spare, not more memory is needed. But at a certain point, I definitely will be adding something where more memory needs to get allocated. On the other hand, changing something that already exists, modifying it in place, does not require more memory, right? And it doesn't matter that 200 is bigger than 1, because under the hood, the integer type is given 32 bytes or whatever it may be that can, hold, I don't know, between 0 and some very big number like 1024, right? And if you all think about Postgres, where there's, I think, the char type and the text type, or int and big int, that's what that exists. Because if I had a really massive integer, and I don't even know if this is big enough, but like 2 times, or I don't know, like 10 to the 50th for scientific computing or something, right? At that point, maybe we have an issue. At that point, maybe we need a different integer type. And at that point, maybe more memory is indeed getting allocated. If I remove something from the list, at a certain point, memory will get deallocated as well. Joseph, yes, sir.
So if it's a 1 byte to store a single number like 2, then how does modifying that number to a triple digit number not take up more bytes?
Yeah, that's a great question. I don't want to go too in depth to this. Let's make a quick diagram. Actually, we'll do it this way. 4, 6, 8. Yeah, let's make a quick diagram. Let's talk a little binary. And I'm not going to go too deep in the weeds, but it's worth talking about at least a little bit. So everything in a computer can either be zero or 1, right? How does an integer get represented in binary? Binary is all about powers of 2. My apologies. Can everyone, is this text size okay? Can everyone see this? Awesome. Right, so we have 8 bits, 1 byte. Can someone remind me, what is 2 raised to the 0th power?
1.
Yeah, anything raised to the 0th power is 1. What's 2 to the 1st power? It's 1, or it's 2. I'm so sorry. Right, like something raised to the 1st power is itself. And I totally missed 2 to the 2nd power, 2 squared, right? What's 2 squared? What's 2 times 2? Not, I know it's an easy question, but not a trick question.
4, or yeah, 4,
Yeah. And what's 2 to the third power?
8,
Yeah. And 2 to the fourth,
16,
2 to the fifth.
32,
Yeah. 2 to the sixth.
64,
Yeah, Chris, love it. And then 2 to the seventh.
128.
Yeah, exactly. And I'm gonna write these out as we go. Right, and so everything is powers of 2. And so, right, the same way like a base 10 system, each digit represents maybe 10 to the first, or if we have, 300, this 3 over here, that represents 3 times 10 to the second. This 0 over here represents 0 times 10 to the 0th, and so on. So in a binary system, we only have 0 or 1. Right, so and the thing, we're not even going to talk about negative numbers. Negative numbers actually take up, I believe, 1 bit when we're doing this. Let's actually talk about negative numbers. We'll do it when we get to the end. Let me throw in a whole bunch of zeros. And I have gone on a bit of a tangent, I know, but the great thing about this is it's really, really straightforward. And then once you know it, a lot of stuff makes sense. Right? In binary, everything can only be 0 or 1. So right now, what number does this represent?
0.
Yeah, exactly. Let's see. Oh, can we make these bigger? A little bit. What is this 8-bit binary number represent?
1.
Yeah, exactly. And in fact, let's make this bigger so that we can just kind of have this up as a reference while we talk about this. Right? Because this is 1 byte, 8 bits. And Len, what does this 8-bit binary number represent?
You sum the bottom 2 numbers, so it'll be 3.
Yeah, exactly. Exactly. And thanks for pointing it out, right? 2 plus 1 gives me 3. What does this 8-byte binary number represent?
67.
Yeah, 64 plus 2 plus 1, 67. So I can actually represent a whole bunch of numbers this way. I remember off the top of my head, but I believe this lets me represent pretty much any number between like 0
127.
and
So it's always
yeah,
1 less than your highest bank.
yeah, 127. And in fact, I have to double check, but we may in fact lose this last spot because this may actually end up representing if this is a positive or negative int.
That is correct.
Yeah. Yeah. And I think it's even called like big endian or little endian, which is it the first or the last bit in 8 bytes that you use to keep track of if your integer is positive or negative? So this is how, with 1 byte with 8 bits, we can store between like 0 and 120 integer values from negative 127 to positive 127. Len, yes, sir.
So when you said big Indian, you're talking about using the 128 bank, and little Indian you said would be like the 1 bank down here.
Yes, I think that's correct.
That's my understanding too. I just wanted to, yeah, to be Googled later. We don't have to look at it right now, but it
Yeah.
was just
Yeah, I don't
putting a
want to
little bit of
rabbit hole
context
too
to the
much.
words while you're talking.
Thank you. Yeah. Yeah. Regardless of the term, basically, like when, designing a computer architecture at a really low level, someone has to decide, do we use the last bit or the first bit to keep track of if this integer is negative or positive? So great question. A little bit of a rabbit hole. I hope, was this useful to folks to kind of dig into this a bit? Cool. I'm not going to go further. But the amazing thing about binary, by the way, is that like binary arithmetic is incredibly simple. I guess I am going further. You literally add the columns up, right? And then this would become a one, and then this would become a one, the same way like we kind of learn to stack stuff up and do addition in school. That's also why it becomes incredibly simple in like really simple like logic circuits to do binary arithmetic. Okay, so this was a bit of a tangent, but now we have a really good answer to the question of how does 1 byte hold an integer value between negative 127 and positive 127? I just want to pause and check in and see if folks have any questions before we keep on rolling. Okay, awesome. There's a little more ground I want to cover, and then we'll pause and switch gears and look at linked lists. So whenever we're doing stuff in Python, some operations require more memory to be allocated, and some don't, right? The different data structures that we get for free in Python work different ways as well. And we've seen a lot of this, so some of this will be a review, but let me go ahead and just comment that out just so it's gone. So can someone remind me, what's the difference between a list? What's one of the big differences between a list and a tuple? Daniel, yes, sir.
A list is mutable and a tuple isn't.
Yeah, exactly. A tuple is immutable. I can't actually change, and let's actually make this a tuple, a value in my tuple once it's created. And the Python standard library sys has a lot of really cool stuff, one of which is this get size of method. And I'm actually curious, I'm pretty sure it returns it in bytes, but Python get size of. Yeah, it returns the size of an object in bytes. It does start to get a little tricky. Only the memory consumption directly attributed to the object is accounted for, not objects it refers to, right? So if I use get size of an instance on my user class, and my user class, has like lists and tuples inside of it, I don't get all of that stuff, right? I just get the immediate object. Other references to other objects aren't included. But let's go ahead and run this code. Can everyone see this all right down here at the bottom? The tuple took up 24 less bytes. 24 is a multiple of 8, by the way, right? Which means that it's a power of 2. So everything is powers of 2. Why did the list take up more? Probably because of all the other stuff that needs to happen with the list data structure. And the fact that since the tuple's immutable, we can represent it more compactly in memory. Right? If I try to modify my tuple, I'll get an error. Unlike with a list. It should still be able to access a tuple by index. But we can't modify it. So this is good to think about. Again, Python does a great job of managing memory, but there will be times where maybe you have to write really performant, efficient code, or you have a massive list. Maybe it's a list of the zip codes of everywhere in the United States, right? And it's never going to change. And I'm going to put it in instead of in the database, because then I have to read it from Postgres every time. And I know I'm never going to be adding any zip codes to there. Or maybe it's like the 2-letter character codes for states. I store it as a tuple, you know. Because it's stored more efficiently in memory and I know I'm only going to ever read from it. So that's actually a good example of where being aware of this can help you make more efficient programs. So it's important to think about, do I need to modify this data or do I just need to read it? Integers versus floating point numbers are another classic where integers take up less memory if I don't need a floating point number. You might work with C#, which is sort of very similar to C++ or Java, where you have to explicitly declare types. Or when you're designing your data models in Postgres, you have to think about this as well. Thinking about doing something inside a loop 1,000 times versus allocating memory once and using a list comprehension. Like another example that's a bit of a classic with this is for I in range. Let's just this is not the best way to do this in Python, but let's just pretend. Let's say we have a big list of names. Let's say for some reason, and in fact, we can just do it for name in names. This code will work. Every iteration of this loop, I'm defining and recreating the same function. And a function takes up memory. If I move that function outside of the loop, right, maybe instead of a loop, we're looking at a class and a function that gets used in there, then the function only gets defined once and called in here. So that's, I think, also a good example of thinking about memory allocation along with like append operations and things like that. Deleting data is less common with Python because the Python runtime does manage it. But if you're dealing with very large amounts of information, we might actually have to use the delete operation. And let's run our code and see what happens here. And let me, oh good, the tuple example's gone. And I get a name error because I've deleted it on line 39. Right? That memory has been deallocated, that variable no longer exists. Again, this is less common to do on a day-to-day basis, but it's important to be aware of. Certainly updating stuff in the database, I think it's important to think about, and just being generally aware of memory usage. And as we've discussed, high-level languages like Python do this for us. So being aware of this, keeping your eye open for maybe opportunities to use a tuple if you're only going to read, understanding, an in-place operation versus an operation that requires more memory, and thinking about where do I want to perform my operations that take up more memory. I would say that about 75% of the time, it's probably not something you'll run into, but stuff like this is a lot more common than you think once you start looking for it, especially say for React components with helper functions. We define a lot of little helper functions in here. And we can do it and it's fine and it's not the end of the world. But if we have a really big React program at a certain point, doing stuff like this, excuse me, I'm so sorry about that, starts to make our program more efficient. And for some reason, my keyboard shortcuts just don't want to, my fingers just don't want to do what I want them to do today. So we've talked about, just to kind of put a bow on things, the different kinds of memory and how it's organized, arrays. In fact, we dug deep into binary, which was awesome. How Python manages memory. Do folks have any questions or things we might want to dig into a bit more before we take a break and take a look at linked lists? Okay, awesome. Folks, why don't we do, we've been going for just over an hour. So let's take a 10-minute break. And then we'll reconvene and we'll look at linked lists, and we should be able to take a short break before retro. Does that sound good to everyone? Okay, awesome, folks. Thank you very much. And I'll see everyone in 10 minutes. All right, so we've talked an awful lot about memory. Now let's talk about linked lists, right? And hopefully this idea of a linked list that we got introduced to, and many of you I know saw it already with LeetCode in your teams, but that we talked about in the last data structures lesson a bit, starts to make more sense, right? Because if this is maybe an array right here, well, the operating system, the computer may not be able to give me contiguous blocks of memory every single time. So if I have related bits of data stored in different places, I need to be able to link them together. And that's what the linked list data structure is, right? Over here, we have the value. And over here, we have the pointer to the next location in memory. I don't have a slide deck for this one, but I do have a TL draw. We talked about how even a single character could take up 1 byte, 8 bits, right? And so a string takes up a lot more. And I don't know how long my string is going to be. Maybe for some reason, maybe for like some natural language processing, for some sentiment analysis that we want our AI code to do, we need to tokenize a string and break it up into individual words. And I don't know how long each one will be. And that's a bit of a contrived example, but it points out the scenario, right? Where we can't put each word inside a whole array for the purposes of this argument. Or again, just imagine we're Netflix and this is how like Lord of the Rings extended edition, which is like 6 hours long, is getting stored on a hard drive somewhere. So a linked list, whether we use a class or a list or a tuple, in the abstract sense, the data structure has 2 parts, right? A node has a value and then a pointer to the next item in the list. And the very beginning of the list is called the head, because without the very first thing in the list, we can't find the next. And so hello world, and here just imagine that that pointer is some random memory address, right? It's sunny. And so I just want to check in because I think linked lists are often like why these things exist can be a point of confusion. Does this help kind of illustrate at like a low level the value that something like a linked list data structure provides now that we've kind of dug into computer memory and arrays a bit? Or do folks kind of feel confused, like why does this exist? Why are we talking about it? And if confused, that's okay, because honestly, I think it can be a bit confusing. Cool. I'm going to take that as we're all feeling pretty good about sort of linked lists on the conceptual level. All right, let's dive into some code. Let me just take a quick look at X-ray questions. So let me go ahead. Let me just make just open up a new file here. And so let's go through and let's build this linked list data structure. There's a couple things that we need to think about with linked lists. Insertion. Insert at head of list or insert at tail of list at the beginning or the end, right? Finding. We have to go through the list in order to find it. We're going to learn in the next lesson about what's called doubly linked lists that can move forward and backwards. But this simple one, we can only go in one direction. You know what I mean? Deleting. We have to find the node we want to delete, remove it, connect the neighboring nodes so the chain isn't broken. So these are the things that we have to think about with linked lists. We wrote some linked list code last week. So let's write this again. It's a very similar implementation, even though it's not quite the same. We're going to need a node class. And the node is going to hold some data or the value. And next is none, right? And this is our reference to the next node in the list. So I can make a couple nodes. But then I still have to connect them, right? And now, if I wanted to, I could maybe loop through them somehow. But this is a bit of a pain. It's a bit of a manual process. There's some management that needs to be involved with this. So instead of doing this, we're going to create a linked list class to do a lot of this work for us. And I just want to pause and check in and see if folks have any questions. Okay, awesome. Let's get our linked list class knocked out and then we'll do some manipulation. And let me just get a quick show of hands. How many people have already done a decent amount of work with linked lists and like the leak code problems you've been doing in your teams? How many people have written code to delete something from a linked list on your own or in your teams? Okay, I see a couple hands. That's totally okay because the team stuff has been very much self-guided. So that's what we're doing this here for today. Honestly, for technical interviews, about 75% of the problems are not even with complex data structures. Maybe 25% of the time you'll hit a linked list. If you do, these are probably the things that might come up. And also you flex a lot of the same skills once we have to start dealing with pointers. So let's go ahead and build this out and talk about it. So I'm going to get rid of these and let's go ahead and make our linked list class. We're going to need to initialize it. And we need to keep track of the very first node in the list, which initially will be set to none. Inserting at the beginning of the list is actually pretty easy. And let's in fact go over to the TL draw and like kind of talk through this conceptually before we build it. So can I get, let me lower my hand. And can I get a volunteer? And can someone explain to me, not with code, but just in plain English, like I'll drive with the TL draw. Can someone else navigate and maybe tell me like, what do we need to do to add something to the head of this list? You know, like maybe, you know, wow, right? So that our sentence becomes, wow, hello world, it's sunny. What are the steps? Well, first I need to create a node, right? It's not going to get added, but I need to create it. So I'm going to borrow this one and duplicate it, and we'll drag it over here. And it's not linked to anything yet. But now my node says Y. Now that I've created my node, let's see here. Maybe Earl John, what's the next thing we have to do with our node once we've created it to add it to the head of the list?
Would we need, I've never really dabbled into linked list, but if I had to guess, would we need to add something in front of it so we can connect it to the head?
Yeah, exactly. Right. And here, I need to point it to the head. And let's see if I can just go back with the TL draw. There we go. Talk about caching. Thank you, TL draw. Oh, and it is either I'm losing my mind and hitting the wrong keyboard shortcut. And I think I was doing Control C, Control D instead of Control C. Yeah, we'll just draw it out manually. Sorry about that. Earl John, you're absolutely correct. We need to make that pointer connection, right? Now, I don't actually need the memory reference, but just like we did before where we had, you know, maybe node 1 equals node hello, and, you know, my new node equals node Y. Earl John, what line of code can I do here just to put new node in front of node 1 to have it point to it.
Oh, would it be the dot next?
Yeah, exactly. Just like we did a moment ago, because Python is a pass by reference language for objects, right? We're passing a reference to the node 1 object in memory. And that's what we're setting next to. And Earl John, thank you very much for quasi volunteering there when I called on you. Right, you know, we can print out the memory location of node 1, but it won't be any meaningful. So we need to create the new node. We need to set. In fact, let's call this new node. In fact, let's do proper Python camel casing like that. And let me go ahead and fix this here. We need to set new node next to point to head node. What's the last thing I need to do to make this complete? How do I find the first element in my brand new updated linked list? Mikhail, yes, sir.
Okay, you gotta set the new node as the new head node.
Yeah, exactly. Right, because I always have to start at the beginning of a linked list. It's not like an array. I can't, there's no my linked list sub 0 or 45 or 4. That doesn't exist. If we don't have the very first node in the list, the head, we're sunk. So we have to update the head. So we have to create our node. We have to set its pointer, and then we have to update head. Do folks have any questions about that? And this, by the way, is how you all should be thinking through the LeetCode problems. We haven't written a line of code. At best, this is pseudocode, but we now understand our algorithm, right? Now let's work on the implementation. And now that we've talked through it, hopefully this feels really simple and obvious. Right? Create new node. Point new node to current head. Update head to be new node. Now, there's an edge case here. What's the edge case scenario that my algorithm does not currently account for? Let's run our code and see what happens. My linked list is a brand new linked list. Let's do my linked list dot insert at beginning. Y, and then let's print my linked list dot head. Before I run this code, does anyone have a prediction about what's going to happen when I run it? No one understands what this code is going to do. I don't believe that at all. Come on, guys. What's this code going to do when we run it? Earl John, yes, sir.
We're just putting it in the beginning as make it as the head.
Yeah, let's walk through it. So we're going to call our insert function. We're going to create our node. we're gonna set new node.next to self.head. And then we're gonna set self.head to the new node. And I think that will work. I hope I didn't misspeak and we don't have an edge case here. Let's in fact print head dot value. And I apologize, guys. I may actually, let's see. Oh, it is not value, it is data. I apologize, Earl John, you were completely correct. I think I got a little confused. I think our edge case comes up a bit later with insert at end. And just to share, what I was worrying about was like, well, if head is none, do we have a problem? Right, but I don't think we have a problem here. And in fact, let's test this out. Let's do another insertion. Let me go ahead and clear this. Right, and let's just very manually do, can someone tell me how can I print out the next thing in the linked list? Well, I can do dot next dot data. Right, and hopefully I don't have that wrong. And there we go. And I just want to, in fact, reverse the order of this. Oh, no, that's correct. I got a little confused about which one we wanted first, but we want Y up front. And we see that we added Y as the head. We added hello, which in fact is not what I wanted, because I actually want my sentence to say Y hello world. So we're gonna have to implement an insert at end function to make that work nicely for us. And then the next one is Y. So let's go ahead, let's implement that insert at end function. So what are our steps here, right? If this is insert at head, what are our steps to insert at tail at the end? Well, we're gonna have to create a node. We're going to have to iterate through the linked list to get to the end. And then we're going to have to have our tail node.next point to new node. Right? Unless we keep track of the tail, which is another implementation that's a bit more complex, but that's not the approach we're going to take. I'm going to take a quick look at this to make sure I have this right. But this is the approach that we're going to follow here to insert at the end, where again, we need to create the new node. And here's where our edge case comes up, and I'm going to make a to-do, and we'll worry about it later, so we can see the error. Now we need to get to the end, the tail of our list. So we need a pointer. I'll call it last node. You'll also see it called tail. Let's start at the beginning. Let's do a while loop. Let's say while there is a next node, move forward. And then when we finally get there, point tail node to new node. Right? And to go through the TL draw, what we're doing here is we need to basically, move all the way to the end and then point to the next thing in our list. So we've inserted at the beginning. Let's change this. Let's actually test it out like this. Let's insert at end. So we got an error here, and this is where I got a little confused, folks, and forgot about an edge case. You got kind of a preview from it with the code from the curriculum. What's the edge case that I'm not handling that's causing this error? Not a trick question. Mickey, what do you think is going on? Oh, Earl John, I appreciate it, but too late. So Mickey, we have this attribution error, none type, object has no attribute next. Why don't you step us through this code starting at line 41 and explain what each line is doing until we hit the error. So what's going on here at line 43?
We're putting a new node at the end that holds data.
Yeah. And is that the line
And-
of code that's throwing our error?
No, because it says,
Yeah, which line I'm throwing
yeah,
a
so it says
massive
last
hint.
node.
Yeah. Line 49 is throwing the error.
Yeah.
Right. So what are your thoughts about what might be the issue here at line 49? What is the value of last node here on line 48?
So self.head, so it's
What is the value of self.head right here on line 58 when we create the linked lists? And let me scroll up a bit and get rid of my annotation code.
up here it says at the top self.head is none.
Yeah, exactly.
So
And have we changed the value of
no, it looks like we've
self.head
just got
anywhere between here and here?
no, so we're just inserting a value of none.
Yeah. So what is the value of self.head right here on line 48 when we execute this method on line 60?
But it's still none,
Yeah, it's not.
I think.
And so,
Yeah.
what's happening on line 49?
So 49 says while last node dot next, we're getting a lot of none equals none, I think.
Sort of. I'm looking, I can't find the thing I wanted. But if we look at the error message, and this is not easy to see because I can't find my, oh, spotlight, perfect.
No, it says there is no attribute dot next.
Right. And that's our error, right? That none doesn't have an attribute dot next. And so
Yeah.
Python is throwing an error and failing. So Mickey, how can we handle this edge case so that we don't have this problem?
We have to assign some sort of value to self dot head.
Yeah. And when does this edge case occur? Does this happen every single time I run insert at end?
if you don't
here, and let me
assign
bring,
any sort of value to the new node.
close. So the deal here, and the reason we're running into this problem is because this is the very first time we're inserting something in the list. Right? Once we already have something in the list, you're correct, we need to update self.head. But once self.head exists, we won't have this problem. Right? So this edge case happens the very first time we insert into an empty list. Does that make sense?
Yeah.
Yeah, exactly. And I probably should have pulled out the debugger because we could have walked through it and seen it that way. The way I learned to do this is we would literally write this on a whiteboard and talk through it line by line like this. And I really think that's the way to learn this stuff. The debugger is great, but you want to build that mental model to be like line by line. This is exactly what the computer's doing. So if
Yeah, it definitely helps me
self.head,
when I'm writing.
yeah, exactly, is none, self.head equals new node, and we can just return. And in fact, let's hop back over to our guide code, because we can in fact clean this up a bit, which I knew we could because my Python, the JavaScript I'm really strong with. Python, I'm always improving my best practice. If self.head, right, evaluates the false or is none, we set it to new node and we return. And let's run our code and see if we have an error now. And now we see it added. Earl John, yes, sir.
Just a quick question. So I see a lot of that, like we're just putting a return without nothing next to it. Is that just saying that return itself?
Great
And like-
question. It will return none. I think we just don't have to type it. I'm
Okay.
pretty sure that's like the default return value. But you raise a good point. Why do we add the return statement on line 49?
So that we're not, just so that like we're not really returning anything if there is nothing in the head, right?
Not quite. If I don't have this return statement, what happens the very first time I insert something into the list with insert at end? Mikhail, yes, sir.
I think you just have that return statement because you don't want to execute line 51 onward.
Yeah, exactly.
Yeah, and I think you could also have been done with like a if else statement. But like the return statement is the same thing. Because you could say if head is none, then you add the head to the new thing, and then you do the else, and then you do that. But the return statement does the same thing as a if else statement.
It does. You will see the people use return a lot because if else is extra conditional logic. So this is a really important pattern to become familiar with. Because return stops execution of this method, right? It returns. So why write an if else that's an extra line of code that I have to think about if all I need is the if statement and a return? Because once you get used to this lets you write very clean and efficient code. And what we really have here are two cases, right? These are the two possible things. These are the two possible states of my list when I'm inserting. Either it's empty or it's got at least one thing. And as you work on leak code problems, thinking about edge cases and the different states is really good to think about. Because like, this is a classic kind of edge case, the very first time we insert something. And Earl John, thank you for digging in on that. And Mikhail, thank you as well. And in fact, we can just do that now. So I just want to check in and see if folks have any questions or parts of this insert at end method it might be good to go over. Cool, let's test this out. So, as you can see, we spent a lot of time walking through it, but this is what you want to do with this stuff, because maybe you get to the final round interview and it's the on-site and it's in person, and they're like, awesome, let's implement a linked list on a whiteboard. But also because this just flexes so many programming muscles. And let's see if, first of all, if this runs without error, and let's do some really lazy printing. Right, there's clearly a better way to do this, but just kind of get the job done. We see that indeed things are being inserted into the list correctly. So traversal, going through the list, is gonna be pretty similar to this code that we just wrote. So let's go ahead and write a little bit of traversal code. I'll kind of leave this up here as a reference. And in fact, we could even maybe add like a callback function. And we need to use our while loop again. And we're gonna iterate through. And what we can do here is we can maybe call our callback and pass it. Actually, that doesn't make sense for printing the list. I apologize. We'll come back to this. But this is a nice way to pass in behavior, right, with linked lists. But let's just print out current node data. Let's add a default setting. So when we get to the last node, we don't get an error, right? The opposite problem that we had before of I get to the very end and it's none. And let's see if, in fact, this does the job. And there we go. And now we're looping through our list, right? And the tricky part with linked lists is always like, I'm going to move on to the next, but we need to handle the edge case. Basically, we either need to stop before we get to none, or if current node gets all the way to none, we have to print out nothing. Right, and that's kind of like the two ways to implement these. And you can see that it's a slightly different approach here because we're checking .next, and here we just loop all the way through to the end, and current node will eventually end up as none. And in fact, if we print current node, I think we can see that happen. So I apologize. I may have gotten confused there on what's happening. Yeah, I apologize, guys. I totally jumped the gun there. I just had Friday brain. This end is just giving us a nice string appending. Our logic, as you can see, is not taking us all the way through to none because we're we check if this has a value or not. So I do apologize for that confusion. Which is also why I love print statements, because if I'm not sure about something, I just throw in a bunch of print statements and run the code. I think we have just enough time to implement deletion. Do folks have any questions before we implement this last method with our linked list? Okay, awesome. So here, again, we're going to need to do a similar process. We're going to need to iterate through the linked list, which can be a little tricky. Check if the node is the one we want. And the tricky thing here is it's like links in a chain, right? Because if I just there we go. If I just delete that, my list is broken, right? If I just find the node I want to delete and delete it, my list is broken. So what am I going to have to do before deleting this node? Earl John, yes, sir.
Wouldn't we need to initialize the last node and then the next node so that we can connect them once we remove that current node that we want to remove?
You have the right idea. Right? If this is the one that we want to remove, and let's give ourselves a little arrow here to point to it, or it can be in red. Right? We've gone through the list. We found this is the node we want to delete. I need to grab the previous list in the list. And point it to the next one. And I need to do that first before I lose that reference, or I need to hold on to both of these, like you were saying, Earl John, and then we can delete it. Right? So that's the step here. Morad, yes, sir.
Yeah, but how can we determine the position
Great
of
question.
this node?
Great question. We're going to use pointers. So as we iterate through, and let me make this one red. And let's make this one green. And let's call this per node. And then our green one, let's call previous node. What we're going to have to do is just like we create over here in our code, right? This is our pointer. Here we call it last node. Here we call it current node. Well, we're going to have to create a second pointer. Because then you're absolutely right, Maura, we have to have that reference to the previous node. Does that help answer your question? Awesome.
Thank you.
And you'll see this technique come up in other things that are data structure and algorithmy, not involving linked lists. You know, I'm sure you all have seen like problems where you have like a pointer at the beginning and the end, and you start moving them towards each other. So that's kind of, I think, some of the programming muscles that these data structures and algorithm type problems flex. And I am just going to have the guide code up here just because I don't want to make an error. And truth be told, this stuff is a bit tricky. And this is why, you know, even like folks who are already in the industry as software engineers, like we're not writing linked lists all day. If I was at a company and had to start interviewing for new jobs tomorrow, I'd have to do some refreshing on linked lists and this pointer logic and stuff. And that's why, like, everyone is like grinding on these leak code problems, and you all will want to as well at graduation. And we're almost at time, but we've talked through this really well, so I think we can now just write code and implement. And then this is really the last thing with linked lists, because we've now walked through all of it, and these are the core activities. So we've got our current node pointer. And here we can just handle if very first node is the one we delete, because this is a bit of an edge case. And the logic is a little different, because we have to update self.head, right? Again, the beginning is when you see edge cases, the end is when you see edge cases. Right, so these are our two cases. We're going to create our previous node pointer and set it to none to begin with. And now we're going to loop. And we're going to go forward through the linked list until the current node is the one we're looking for. And we're going to have to move the previous node forward. We're going to have to move our pointers forward. And then we have to delete undesired. Oh, I'm so sorry. We have to handle if node not in list. I believe this is what this edge case is doing. And now we finally delete without breaking the chain. And let's just deallocate memory, because this actually removes it from the linked list, right? I don't actually need to do anything with that node that we want to delete once it's removed from the list. Well, it didn't quite grab the whole thing, but I think you guys know what I mean. But like we were talking about in the earlier part of the lesson, we want to do good memory management, and we might be using this all the time. So we're going to do current node equals none. Frankly, there's a couple ways to do it. It's also not the worst idea to return the current node sometimes if you delete. We could also use the delete method, but this is a very good way to do it. And that is deleting a node. So I think we hit time. I think there's enough time for one question, and then we can take a short break and dive into retro. Is there any particular part of this code here that might be good to walk through to talk about the logic of what's happening when we delete a node from our linked list? How are we feeling on sort of like the logic of what this is doing and the edge cases we have to think about? Good. So I need to see the code again. What's the vibe? I see a bit of a mix. Yeah, so the thing with this is it just takes a little bit of practice. And we have a couple assignments for you in leak code. I've also added an article I really like that goes through computer memory. That I stole some of these images from, but it just goes into more depth on stuff. And I think they've done a really good job of summarizing it. I've also added a book to our lectures and notes that I'll send out some pages on that go very much in depth for anyone that's interested in memory. All right, folks, thank you. Let me go ahead and stop the recording.